Okay, so let's try problem 4.1 from Wald's General Relativity. He wants us to show that Maxwell's equation 4.3.12 implies strict charge conservation. So in other words, we have 4.3.12, which tells us that nabla A on FAB, where FAB is the electromagnetic tensor, this is minus 4 pi JB. And we want to show that this implies, show that this implies that nabla A JA equals 0. Okay, so we can start by taking a covariant derivative of both sides of this equation. So we'll get something like nabla B, nabla A, FAB equals, and then the covariant derivative is going to pass through the constants, of course, and we get nabla B, JB here. Now, just, I'll do this off to the side, but so that we remember, nabla B, JB is nothing other than nabla A, B, nabla B, nabla A, JB, but we can pass this through and say this is equal to nabla A, GAB, JB, since the covariant derivative of the metric is 0, and this tells us that we get nabla A, JA, so these two are equivalent. So we are able to rewrite this. We can rewrite this entire equation here like this. Minus 1 over 4 pi is equal to times nabla A, nabla B, nabla A, FAB is equal to nabla B, JB, or as we've shown, this is equivalent to nabla B, JB. So really at the end of the day, if we're able to show that nabla B, nabla A, FAB equals 0, then we've done what the problem has asked. In fact, we're going to approach it a little bit differently even, but let's just go ahead with it. So we're going to take our original equation and add it to itself with the indices flipped to start. So we get nabla B, nabla A, FAB. Remember, this is just from right here. And then we're going to add it with the indices flipped. So it's adding the same thing essentially. A, nabla B, FBA. And this is going to equal minus 4 pi times nabla B, JB plus nabla A, JA. We'll say those are just going to add together and be the same thing though. So we get equals minus 8 pi nabla B, JB, we'll say. And so showing that this is equal to 0 is just as good. So since the electromagnetic tensor is antisymmetric, in other words, FAB is minus FBA, we can rewrite this as nabla B, nabla A, FAB minus nabla A, nabla B on FAB, just so we get the same tensor there and we can actually pull it out. So B nabla A, minus nabla A, nabla B, FAB equals minus 8 pi nabla B, JB. So let's just examine this left-hand side here. We can pull a minus sign out and put it in this order instead. So the nabla A, nabla B comes first. Times FAB. Now, we can use metrics to lower all of the covariant derivative indices and then raise those same indices on f. And I'm not going to do this explicitly. I'm just going to write this out in the flipped form. So like this. FAB upstairs. Now we're able to rewrite this in terms of the Riemann tensor. We could do this by recalling this relation with covariant derivatives on an arbitrary tensor field. So by using this relation that we have here, our left-hand side is able to be rewritten in terms of the Riemann tensor like this. Get a negative r, a, b, e, a, f, e, b, minus r, a, b, e, b, f, a, e. Okay, so we can let the minus sign distribute here. So we end up with r, a, b, e, a, f, e, b, plus r, a, b, e, b, f, a, e. And furthermore, the second term can be rewritten as a Ricci tensor. So let's say r, a, b, e, a, f, e, b, plus r. There's a contraction over the b's, so we get r, a, e, f, a, e here. So now the idea is we just want to get this first term in a similar form as with a Ricci tensor, and matching indices on the electromagnetic tensor. So to do this, we'll use the antisymmetry of the Riemann tensor in the first two indices. So to get minus, r, b, a, e, a, and now we have that contraction over the a's in the second and fourth indices, f, e, b, plus r, a, e, f, a, e. So we can rewrite this now as r, b, e, f, e, b, plus r, a, e, f, a, e. Now remember that the Ricci tensor here is symmetric, so we can say this is minus r, e, b, f, e, b, plus r, a, e, f, a, e. And then if we just rename the dummy indices to match, let's say a and e again, we see that these cancel with one another, and this equals 0, thus completing the proof.